Imagine waking up one morning and discovering that everything you thought you knew, every textbook, every theory, every scientific model built over a century of brilliant human effort, might be missing something fundamental. Not wrong in a small way, not off by a tiny margin, but missing something so enormous, so deeply structural, that the very framework we use to understand our own existence needs to be revisited. That is the situation astronomers found themselves in when the James Webb Space Telescope opened its golden eye and stared into the deepest, oldest corners of the universe. And what it found there, in that ancient light, in those impossibly distant galaxies, in those mysterious red dots scattered across the early cosmos, was something that made scientists, brilliant, careful, methodical scientists, stop and say words they rarely ever say. We were not supposed to find this. This is not a story about a telescope breaking down or a mission going wrong. This is something far more unsettling. This is the story of a telescope that worked perfectly, captured data with extraordinary precision, and then handed that data to the finest minds in astronomy, and those minds stared at the results, checked them again, ran the numbers a third time, a fourth time, a fifth time, and came to a deeply uncomfortable conclusion. The universe is not behaving the way we thought it would, not in a minor way that can be explained by measurement error or calibration problems, in a way that strikes at the very core of our cosmological understanding, in a way that suggests our standard model of how the universe was born and how it evolved over nearly 14 billion years might be incomplete in ways we are only beginning to understand. Think about that for a moment. The standard model of cosmology, the Lambda CDM model, is one of the greatest intellectual achievements of the 20th and 21st centuries. It describes how the universe emerged from the Big Bang, how matter gradually clumped together under gravity, how the first stars ignited, how galaxies slowly assembled themselves over hundreds of millions of years, and how dark matter and dark energy shaped the cosmic landscape we see today. This model is supported by decades of observations, by the cosmic microwave background radiation, by the distribution of galaxies across vast cosmic scales, by the abundance of light elements like hydrogen and helium. It is not a guess. It is not speculation. It is the product of painstaking scientific work spanning multiple generations of researchers. And yet, when James Webb turned its gaze to the earliest epochs of cosmic history, what it found did not match the predictions of this beautifully constructed model in ways that are deeply significant and still not fully resolved. Before we go any further, stop and ask yourself this question. If you could build a machine, any machine, using the most advanced technology humanity has ever developed, and point it at the night sky, and use it to look back 13.5 billion years in time, back toward the very moment of creation itself, what would you expect to see? The Big Bang happened roughly 13.8 billion years ago. In the very first moments after the Big Bang, the universe was an unimaginably hot, dense, seething plasma of particles and radiation. As it expanded and cooled, atoms formed, then clouds of gas, then the first stars, then the first galaxies. The whole process of galaxy formation was supposed to be slow, gradual, like watching a child grow into an adult. You need time. You need years. You need generations. A galaxy takes hundreds of millions of years, maybe even a billion years, to properly assemble itself. That was the prediction. That was what the model said we would find. Small, faint, irregular, chaotic proto-galaxies in the early universe. Young, stumbling structures still figuring out how to organize themselves. That is what every simulation, every computer model, every theoretical prediction told us we would see when we finally had a telescope powerful enough to look that far back. James Webb looked, and what it saw was something else entirely. And if you find yourself leaning forward right now, if that question is already forming in your mind, what did it actually find? Then you are exactly where this story needs you to be. Stay with it. Because what comes next involves not one surprise, not two, but a series of discoveries that have collectively made cosmologists around the world do something very unusual. They have begun to publicly wonder whether something fundamental is missing from our picture of the universe. Not wrong, not broken. Missing, and that distinction matters enormously, as we will explore together in the depths of this story. But first, let us understand the instrument at the center of all of this. Let us understand what James Webb actually is, because without that understanding, you cannot fully grasp the magnitude of what it has done. The James Webb Space Telescope is the most complex and ambitious scientific instrument ever sent into space by human beings. That sentence alone deserves a moment of reflection. Not the most complex instrument of its decade, not the most ambitious telescope of its generation, the most complex instrument ever launched into space. Full stop. And it almost did not make it. The story of how this telescope came to exist is itself a story of extraordinary human persistence, of scientific vision stretched across decades, of budgets that ballooned far beyond initial estimates, of technical challenges that seemed insurmountable, and of a launch that the entire global astronomy community watched with a mixture of barely concealed terror and desperate hope. The idea for the telescope that would eventually become James Webb was first seriously proposed in 1996, in the aftermath of the Hubble Space Telescope's own troubled launch and miraculous repair. Hubble had shown scientists something profound, that space-based observatories, when they work, are transformative. Hubble's famous deep-field images, those tiny patches of sky packed with thousands of galaxies, each galaxy containing hundreds of billions of stars, had permanently changed the way humanity thought about its place in the cosmos. But Hubble also had limits. It was designed primarily to observe invisible and ultraviolet light. It could see far, but not far enough. There was a wall in time beyond which Hubble's vision blurred and faded. A wall beyond which the very earliest galaxies hid in a darkness that Hubble's instruments could not penetrate. Scientists needed something fundamentally different. Something that could see in infrared light, because light from the very earliest universe, light that has been traveling for over 13 billion years, light that has been stretched by the expansion of the universe itself, arrives at our telescopes redshifted into the infrared spectrum. To see the dawn of cosmic time, you need infrared eyes. Hubble does not have those eyes. James Webb does. The telescope was named in 2002 after James Edwin Webb, who led NASA during the Mercury and Gemini programs and the formative years of the Apollo program. The naming was not without controversy in later years, but the instrument itself proceeded through decades of development. 25 years of engineering, of redesign, of delay, of budget overruns that pushed the total cost to approximately $10 billion. That number bears repeating, $10 billion. It is the most expensive single scientific instrument ever built. And yet, if you understand what it was built to do, if you understand the questions it was designed to answer, $10 billion begins to feel like a reasonable price for what humanity was reaching for. The telescope's design is unlike anything that came before it. Its primary mirror, the golden hexagonal surface that collects light from the cosmos, is 5 meters in diameter, composed of 18 individual hexagonal segments, each coated with a microscopically thin layer of gold. Gold, because gold reflects infrared light more efficiently than any other coating scientists could use. When fully deployed, this mirror is so large that it cannot fit inside any rocket fairing in its unfolded state. The entire telescope had to be designed to fold up, folded like an origami masterpiece of engineering, fold up into a package compact enough to fit inside the Ariane 5 rocket that would carry it to space, and then unfold once free of Earth's atmosphere. This unfolding process involved 50 major deployment events, 178 separate release mechanisms, and over 300 single-point failure items. A single-point failure item means a mechanism where, if it fails, the entire mission is lost. 300 of them. 300 places where one small thing going wrong meant $10 billion and 25 years of effort would float uselessly in space, pointed forever at a universe it could not see. Launch day was December 25th, 2021, Christmas Day. There is something almost poetic about that date, something fitting about humanity sending its greatest eye into the cosmos on a day of wonder. The rocket lifted off from the Guiana Space Center in Kourou, French Guiana, at 7:20 in the morning local time. Across the world, scientists, engineers, astronomers, and space enthusiasts watched their screens and held their collective breath. The launch itself went smoothly. The Ariane 5 performed exactly as designed, placing James Webb on a trajectory toward its destination, the second Lagrange point, or L2. A gravitational sweet spot located approximately 1.5 million kilometers from Earth in the direction away from the Sun, where the gravitational forces of Earth and Sun balance in a way that allows a spacecraft to orbit with minimal fuel expenditure. From L2, the telescope would have a stable, thermally calm environment, shielded from the heat of both the Sun and the Earth by its enormous 5-layer sunshield, a structure the size of a tennis court made of a film called Captain, with each layer separated from the next by vacuum to prevent heat conduction. After launch came what NASA engineers called the 29 days on the edge. The journey to L2 took approximately a month, and during that month, the telescope had to unfold itself. The sunshield had to deploy and tension. The secondary mirror had to swing into position. The side wings of the primary mirror had to unfold and lock. Each step had to happen in the right sequence, in the right order, at the right time. Mission controllers at the Space Telescope Science Institute in Baltimore watched every telemetry signal, every temperature reading, every motor current, knowing that any anomaly could mean catastrophe. On day 13, the primary mirror's side wings began to unfold. The first wing locked into place. The second wing locked. The primary mirror was now fully deployed for the first time. A 5-meter golden eye, open in space, ready to see the universe as it had never been seen before. On January 24, 2022, James Webb arrived at L2. The months that followed were dedicated to alignment, calibration, and commissioning, a painstaking process of adjusting the mirror segments with nanometer precision, of testing each scientific instrument, of verifying that every system was performing within expected parameters. And here, in one of the first genuine surprises of the mission, the news was extraordinary. The telescope was not just performing within expected parameters, it was performing beyond them. The launch had been so precise that Webb had used far less fuel than planned during its trajectory correction maneuvers. The original design lifetime of the telescope was 10 years. The fuel savings from the precise launch meant the telescope could operate for 20 years, perhaps more. Scientists who had spent careers waiting for this instrument suddenly realized they had been given a gift even more generous than they had hoped. The first official science images were released on July 12, 2022, with a preview the evening before, when President Biden stood before a giant screen at the White House and unveiled what was called Webb's first deep field, an image of the galaxy cluster SMACS 0723, a smear of light containing thousands of galaxies, some of them appearing as arcs and streaks because their light had been bent and magnified by the gravity of the massive cluster in the foreground. The image covered a patch of sky no larger than what you would see looking through a grain of sand held at arm's length. And in that tiny grain of sand of sky, there were thousands of galaxies, each containing hundreds of billions of stars, some of them so distant that their light had been travelling for over 13 billion years before it reached Webb's golden mirror. It was, by any measure, one of the most profound images ever captured in human history. The scientific community reacted with awe. But the awe was followed quickly by something else. Confusion. Because as the first batches of scientific data began to flow in, as astronomers around the world began analysing Webb's observations, patterns began to emerge that did not match the predictions, and not in minor ways. In ways that scientists struggled to explain, in ways that sent theoretical physicists back to their whiteboards and computational cosmologists back to their simulation codes. To understand why those patterns were so surprising, so alarming even, you need to understand what scientists expected to find when they looked at the early universe. The framework that governs modern cosmology is called the Lambda CDM model, where lambda stands for the cosmological constant, which is associated with dark energy, and CDM stands for cold dark matter. This model describes a universe that began with the Big Bang approximately 13.8 billion years ago, expanded and cooled, and saw the gradual formation of large-scale structure driven by the gravitational pull of dark matter, which itself forms an invisible cosmic scaffolding upon which normal matter, the atoms and molecules and stars and planets we can see, slowly accumulates. According to Lambda CDM, galaxy formation is a hierarchical process. Small structures form first. Dark matter halos, regions where dark matter has gravitationally concentrated, begin to appear. Gas falls into these halos, cools, condenses, and eventually forms stars. These small early galaxies then merge with each other, gradually building up larger and larger structures over cosmic time. The process is slow because it takes time for matter to gravitationally concentrate, time for gas to cool, time for stars to form and enrich their surroundings with heavy elements through supernova explosions, time for the whole beautiful engine of galaxy evolution to spin up to full speed. The universe at 500 million years after the Big Bang, according to Lambda CDM, should contain mostly small, irregular, faint, recently assembled proto-galaxies. Young structures. Cosmic infants. This was the prediction that every simulation supported. This was the theoretical landscape that decades of Hubble observations and everything that came before Hubble seemed to confirm. Scientists were confident in this picture. Not blindly confident, not arrogantly confident, but confident in the way that scientists are when a model has been tested repeatedly and found to be consistent with all available data. Lambda CDM had passed every test that observational technology could throw at it. It described the large-scale structure of the universe with remarkable accuracy. It predicted the distribution of galaxies across cosmic scales. It correctly described the acoustic oscillations imprinted in the cosmic microwave background radiation, that ancient glow of light left over from the Big Bang, observed with extraordinary precision by the Planck satellite. Lambda CDM was not just a good theory. It was the best theory available, supported by the weight of evidence accumulated over half a century of modern cosmological research. Then, James Webb looked at the early universe. And the early universe did not look like what Lambda CDM predicted. The first serious alarm bells were raised in early 2023, when a paper published in the journal Nature by Ivo Labe of Swinburne University of Technology and colleagues presented observations of 6 candidate galaxies detected in Webb's early data. These galaxies existed between 500 and 700 million years after the Big Bang, a period when the universe was only about 3 to 5% of its current age. That alone would have been remarkable, because Hubble had never been able to see objects this distant with such clarity. But the distance of these galaxies was not the issue. The issue was their mass. These galaxies appeared to be extraordinarily massive, comparable in total stellar mass to our own Milky Way galaxy, which contains hundreds of billions of stars and has had roughly 13 billion years to build itself up to its current size. One of the objects in the Labe study appeared to contain as many stars as the Milky Way, but was 30 times more compact, crammed into a fraction of the volume. And all of these galaxies existed at a cosmic epoch when, according to Lambda CDM, the universe should not yet have had enough time to assemble structures this large. Joel Leher, an assistant professor of astronomy and astrophysics at Penn State University, was one of the co-authors of that paper. He is a careful scientist, not given to hyperbole. And yet his words when describing the initial discovery have been quoted widely, and for good reason. These objects are way more massive than anyone expected, he said. The paper's results suggested that the stars in these early galaxies had masses up to 100 times greater than what existing models predicted for that epoch. Leher and his colleagues spent months trying to find an error. They checked their photometric redshift estimates, they scrutinized their stellar mass calculations, they looked for contamination in the data, they tested alternative explanations. My first thought was we had made a mistake and we would just find it and move on with our lives, Leher said. But we have yet to find that mistake, despite a lot of trying. He and his team began informally calling these objects universe breakers, a term that quickly captured the attention of the global scientific community and the media. We've been informally calling these objects universe breakers, and they have been living up to their name so far, Leher said. Erica Nelson, an assistant professor of astrophysics at the University of Colorado Boulder and another co-author, captured the strangeness of the situation with disarming simplicity. It's bananas. You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. That word should is doing an enormous amount of work in that sentence. It is carrying the weight of decades of theoretical modeling, of thousands of computer simulations, of the accumulated scientific consensus about how galaxies grow. And what James Webb was showing was that the universe, at least in these 6 objects, seemed not to have received that memo. Now, it is important to be precise here, because precision matters enormously in science. These 6 galaxies were initially detected using photometric redshifts, estimates of their distances based on how their light is distributed across different wavelength filters. Photometric redshifts are useful but approximate. The more reliable method is spectroscopic redshift measurement, where a spectrum of the galaxy's light is captured and analyzed for specific chemical signatures that can pin down the distance with much greater precision. Not all of the initial LABI sample has been fully confirmed spectroscopically, and some of the initial mass estimates have been revised downward as more careful analysis has been applied. The scientific community responded to the initial reports with appropriate caution, and the process of careful follow-up analysis has been ongoing ever since. Subsequent work suggested that some of the apparent overabundance of massive galaxies might be at least partially explained by factors like contamination from active galactic nuclei, essentially supermassive black holes at the centers of these galaxies that were making them appear brighter and therefore more massive than they really were. There is also the possibility that some objects interpreted as very distant galaxies are actually closer, dusty objects whose colors have been mistakenly interpreted as signatures of extreme redshift. A study published in February 2024 by researchers at Johns Hopkins University and the University of Texas at Austin investigated whether the overabundance of ultramassive early galaxies could be explained by modifying the lambda CDM model, specifically by increasing the amplitude of density fluctuations in the very early universe, which would theoretically allow more matter to clump together more quickly, allowing massive galaxies to form sooner. The conclusion was revealing: you cannot simply adjust the cosmological model enough to explain this abundance problem without also creating inconsistencies with other observations. As Julian Muoz, assistant professor of astronomy at UT Austin and co-author of the study, explained, the fluctuation that would make more ultramassive galaxies would in theory create more of the smaller ones too. But that's not what we see. This means that simply tweaking the parameters of lambda CDM does not make the problem go away. It may shift it, but it does not resolve it. Something more fundamental may need to be reconsidered about how the first massive galaxies assembled themselves so quickly after the Big Bang. But here is where the story takes an important turn that deserves full attention. While the initial Universe Breakers announcement was dramatic and scientifically significant, subsequent analysis has complicated the picture in important ways. A NASA press release from early 2025 noted that Webb findings suggested early galaxies were not quite as extraordinarily massive as the first estimates implied. Follow-up spectroscopic observations have revised some mass estimates downward, and the most extreme initial claims have been somewhat moderated. However, and this is a critical however, even the revised picture is not clean. Even accounting for measurement uncertainties, systematic errors, and alternative explanations, there remains a genuine excess of massive, well-formed galaxies in the early universe compared to what Lambda CDM predicts. The problem has not been solved. It has been refined, made more precise, and made more nuanced, but it has not gone away. What scientists feared in 2022 and 2023 was not that a single measurement was wrong, but that the systematic pattern across many observations was pointing to something real, something that the standard model does not fully account for, and that fear has not been put to rest. There is another layer to this story, one that is perhaps even more technically complex, but equally profound. Within the population of early galaxies observed by Webb, astronomers began noticing something very peculiar about a particular class of objects. These objects appeared as small, compact, intensely red points of light in Webb's images. Not the extended, irregular shapes typical of young galaxies, but almost dot-like in their appearance. Brilliant and red. By 2023, hundreds of these objects had been identified in Webb's data, and they were given the informal name Little Red Dots. Hundreds of these objects existed across the early universe, and their nature was deeply puzzling. Were they compact galaxies with extremely high star formation rates? Were they active galactic nuclei, powered by rapidly accreting supermassive black holes? Were they something entirely new, something that didn't fit neatly into existing categories? The mystery of the little red dots deepened as more observations accumulated. In September 2025, a study led by researchers from Penn State University and the Max Planck Institute proposed a startling new hypothesis: that these little red dots might represent an entirely new class of astronomical object, something never previously observed. The researchers suggested that they might be what could be called black hole stars, exotic objects in which a supermassive black hole is surrounded by a thick, bloated stellar atmosphere, a situation that could only exist under the extreme conditions of the very early universe. According to this model, in the dense, hot conditions that prevailed in the first billion years after the Big Bang, a massive black hole could form and then be surrounded by an envelope of gas so thick and so energetically supported that it would behave almost like an extremely massive, bloated star. The researchers described these as representing a new cosmic species, a category of object that the universe apparently created in its youth and that no longer exists in the cosmos as we observe it today, having since evolved into more familiar structures. This hypothesis remains under active investigation and has not been conclusively established, but the fact that it is being seriously proposed in peer-reviewed scientific literature speaks volumes about how far Webb's observations have pushed our understanding of the early universe beyond its comfortable boundaries. The black holes associated with these little red dots are themselves part of a broader and deeply challenging problem that Webb has illuminated with remarkable clarity. This is the problem of early supermassive black holes, or rather the problem of how they got so large so quickly. Supermassive black holes, the kind that sit at the centers of most large galaxies, including our own Milky Way, are objects of truly incomprehensible scale. The black hole at the center of the Milky Way, called Sagittarius A, has a mass of approximately 4 million times the mass of the Sun. The most massive black holes known in the nearby universe have masses billions of times greater than the Sun. These are not small objects. They are among the most extreme concentrations of matter and energy in the known universe, and growing them takes time. There are physical limits, described by a quantity known as the Eddington luminosity limit, on how rapidly a black hole can accrete matter and therefore grow in mass. A black hole growing at the theoretical maximum rate, eating matter as fast as physics allows, still needs hundreds of millions of years to grow from a stellar mass seed to a supermassive giant. Here is the problem. James Webb, in combination with NASA's Chandra X-ray Observatory, found a supermassive black hole that had already reached a mass of between 10 million and 100 million solar masses just 470 million years after the Big Bang. The galaxy where this black hole lives is called UHZ1, and it is located 13.2 billion light-years from Earth. meaning that the light Webb captured from it left this galaxy when the universe was less than 3% of its current age. The discovery of UHZ1 was reported in a paper published in Nature Astronomy in November 2023, led by Akos Bogdan of the Harvard-Smithsonian Center for Astrophysics. The mass of this black hole at such an early cosmic epoch is so extraordinary that Bogdan and his colleagues believe it represents the first detection of what theoretical astrophysicist Priyamvada Natarajan of Yale University had predicted in 2017, a so-called outsize black hole. A black hole that has grown so fast that its mass rivals the total stellar mass of the galaxy it inhabits. In the nearby universe, supermassive black holes typically contain only about 0.1% of the stellar mass of their host galaxies. They are enormous, but dwarfed by the combined mass of all the stars around them. The black hole in UHZ1, by contrast, is as massive as all the stars in its host galaxy combined. How does a black hole grow this massive in just 470 million years? The mainstream answer among theorists is that it did not start from a normal stellar mass seed black hole, the kind formed when a massive star explodes in a supernova at the end of its life, leaving behind a remnant with a mass of perhaps 10 to 100 times that of the Sun. Starting from such a small seed and growing to tens of millions of solar masses in 470 million years requires accretion at or above the Eddington limit for essentially the entire period, which is physically implausible and has never been observed. The alternative, which Natarajan and others have long proposed, and which the UHZ1 discovery seems to support, is that some supermassive black holes in the early universe formed not from stellar mass seeds, but through the direct collapse of massive clouds of primordial gas, clouds that, rather than fragmenting into stars, collapsed directly into black holes, with initial masses of perhaps 10,000 to 100,000 solar masses. Starting with such a heavy seed makes the subsequent growth to supermassive scale more physically feasible. The UHZ1 discovery is described by Natarajan as the best evidence yet obtained that some black holes form from massive clouds of gas. Even so, even with heavy seeds and maximum accretion rates, the timeline is extraordinarily tight. And UHZ1 is not alone. Webb has found evidence of numerous supermassive black holes in the early universe, and the systematic pattern of these objects being more massive relative to their host galaxies than the current epoch suggests is a genuine challenge to our understanding of how black holes and galaxies co-evolved. The overmassive black hole problem, as researchers now call it, is directly linked to the massive galaxy problem discussed earlier. In fact, they may be aspects of the same underlying phenomenon. If black holes in the early universe were disproportionately large relative to their host galaxies, they would have had a profound effect on the galaxies themselves, heating and expelling gas, quenching star formation, shaping the overall structure of the galaxy in ways that differ from what we observe in the nearby universe. Some researchers have proposed that the reason some early galaxies appear so massive in Webb's images is precisely because they contain overmassive active black holes whose radiation is boosting the apparent luminosity of the galaxy, making it look more massive than it actually is based on its stars alone. This is one of the ongoing areas of investigation, and it illustrates how the different anomalies Webb has uncovered are interconnected. They are not isolated puzzles, but potentially different facets of the same deeper mystery about how the first generation of massive structures in the universe assembled themselves. There is something deeply human about the discomfort that all of this creates for the scientific community. These are not abstract theoretical concerns. They are empirical observations, real data captured by a real telescope from real objects in the real universe that stubbornly refuse to fit neatly into the models that scientists have spent decades developing and refining. And the response of the scientific community to this discomfort has been admirable. Not denial, not dismissal, but careful, methodical follow-up. More spectroscopic observations. More refined mass estimates. More sophisticated modelling. The peer review process, slow and sometimes frustrating as it is, serves exactly this purpose, filtering the extraordinary claims through a rigorous process of independent verification, ensuring that before any conclusion is accepted, it has been subjected to the harshest possible scrutiny by the best qualified critics. Now we turn to the second great fear that James Webb has amplified, a fear that existed even before the telescope launched, but which Webb was specifically expected to help resolve. This is the Hubble tension, one of the most significant unsolved problems in modern cosmology, and understanding it requires a brief journey into the history of how we measure the expansion of the universe. In 1929, Edwin Hubble made one of the most consequential discoveries in the history of science. By measuring the distances to nearby galaxies and comparing those distances with the speeds at which the galaxies were moving away from us, measured using the Doppler effect, the same principle that makes a passing ambulance's siren shift in pitch, Hubble discovered that the universe is expanding. The farther a galaxy is from us, the faster it is receding. This observation, combined with general relativity, led directly to the concept of the Big Bang. If the universe is expanding today, then running the clock backward leads to a state of infinite density and temperature at a finite moment in the past. The rate of this expansion, how fast the universe is expanding today, is described by a quantity called the Hubble constant, usually written as h-nero. It is measured in units of kilometers per second per megaparsec, which essentially means for every 3.26 million light-years of additional distance between you and a galaxy, that galaxy is receding from you at h-nero kilometers per second faster. Getting a precise value for h-nero has been one of the central challenges and obsessions of cosmology for nearly a century. Hubble himself estimated the value at 500 kilometers per second per megaparsec. We now know this was wildly wrong, partly because his distance measurements were inaccurate, partly because the Cepheid variable stars he was using were actually two distinct populations that he was conflating. Over decades of improving observations, the value was revised downward, eventually settling in a range between 50 and 100. Two rival teams in the 1990s, one led by Sandage and Tamman, and one by de Vaucouleurs, famously gave incompatible values of approximately 50 and 100 respectively, and spent decades arguing about who was right. The launch of the Hubble Space Telescope in 1990 was partly motivated by the desire to settle this argument, and in 2001. A major program led by Wendy Friedman, then at the Carnegie Observatories, produced a measurement of 72.8 km/MPC. That felt like progress. The disagreement was narrowing. Then came the era of precision cosmology. Starting in the early 2000s, scientists developed a second, entirely independent method of measuring h-nero. Rather than measuring the distances and velocities of nearby objects directly, the so-called distance ladder approach, they could instead look at the cosmic microwave background radiation, the ancient glow of heat left over from when the universe was approximately 380,000 years old and the fog of hot plasma finally cleared enough for light to travel freely. The CMB encodes an extraordinarily precise snapshot of the universe at that early moment, and by analysing the detailed pattern of temperature fluctuations in the CMB, the acoustic oscillations imprinted in that primordial light, scientists can infer the composition and geometry of the universe. They can then take that information, plug it into the equations of general relativity and the lambda CDM model, and calculate what h-nero must be today if the model is correct. The Planck satellite, which mapped the CMB with exquisite precision between 2009 and 2013, gave a value of h-nero Sol 67.4 0.5 km/MPC. Meanwhile, Adam Ries of Johns Hopkins University, one of the Nobel Prize-winning discoverers of dark energy, was leading a team that was continuously refining the direct distance ladder measurement of h-nero. His team's value, using Cepheid variable stars and Type 1a supernovae, kept coming in around 73 km/MPC. When compared to the Planck value of 67.4, this represents a discrepancy of about 8 to 9%. That may not sound like much, but in modern cosmology, where measurements have become precise enough that a 1% uncertainty is considered large, an 8 to 9% discrepancy between two independent high-precision measurements of the same fundamental quantity is genuinely alarming. It is the equivalent of two equally reliable rulers measuring the same table and getting results that differ by nearly a centimetre when the rulers are precise to the millimetre. Something is wrong. Either one or both measurements contain a systematic error that has not been identified and corrected, or the lambda CDM model itself is missing something, some additional ingredient in the universe that affects its expansion rate in a way that the model does not account for. This is the Hubble tension. And it is not a new problem. It existed before James Webb was launched. But scientists had hoped that Webb, with its superior infrared sensitivity and its ability to observe Cepheid variable stars in more distant galaxies with far greater clarity than Hubble, would be able to identify the source of the tension, to find the systematic error that one or both teams had been making, and thereby resolve the discrepancy. Instead, what Webb found has made the situation significantly more complicated, and, in some ways, more worrying. Rios and his team were among the first to use Webb for Hubble constant measurements. They used Webb's infrared camera to observe Cepheid variable stars in nearby galaxies, specifically to test whether the crowding problem, the tendency of Cepheids near the bright centers of galaxies to be measured incorrectly because their light is blended with that of neighboring stars, was responsible for the discrepancy. Cepheid stars are important because they are standard candles. Their intrinsic brightness is directly related to their pulsation period, so by measuring how fast they pulsate and how bright they appear, astronomers can calculate how far away they are. Rios and his colleagues had always argued that their Cepheid measurements were reliable, but Friedman and others had raised concerns about crowding affecting the measurements. Webb's sharper infrared vision cut through the crowding problem far more effectively than Hubble. When Rios compared his Hubble and Webb Cepheid measurements, the result was phenomenal agreement, according to team member Gagandeep Anand. Webb confirmed that the Hubble Cepheid measurements were correct. Rios's value of H-Nero did not change. It remained at approximately 73 kms MPC. The higher value, the one in tension with Planck, the Hubble tension, rather than being explained away as a measurement artifact, had survived the test of Webb's superior precision. Friedman's team, meanwhile, took a different approach. Rather than relying solely on Cepheids, they used Webb to observe 3 different types of distance indicators in 11 galaxies, Cepheids. Tip of the red giant branch stars, known by the acronym CHAR-GB, referring to the characteristic sudden change in brightness that occurs when elderly red giant stars ignite helium in their cores, and a newer class of distance indicators called JAGB stars, which are carbon-rich giant stars with unusually stable infrared luminosities. The advantage of CHAR-GB and JAGB stars is that they live in the outer, less crowded regions of galaxies, making them less susceptible to the crowding problem. Friedman's team worked in a blind fashion, with 3 subgroups each analysing a different distance indicator without knowledge of the other's results, then revealing all results simultaneously in a dramatic March 2024 meeting at the University of Chicago. The results were not what anyone had hoped for, in the sense that they did not deliver a clean resolution to the tension. The JAG stars gave H-Nero Dal 67.96 km/MPC, essentially identical to the Planck prediction, suggesting no tension. The CHAR-GB stars gave 69.85 km/MPC, slightly higher, but closer to Planck than to Rios. The Cepheids gave 72.05 km/MPC, with significant uncertainty depending on assumptions made about the stars, a range from 69 to 73. The 3 methods gave 3 different answers. The average value, combining all 3 methods and their uncertainties, came in at around 69.96 km/MPC, a number that overlaps, within its error bars, with both the Planck prediction and Rios's higher value. The tension had not been clearly resolved. Instead, what Friedman's results seemed to show was a tension within the local measurements themselves, a disagreement between different distance indicators that suggests either that some of the methods have unrecognized systematic errors, or that the universe is more complicated than any of these methods assumes. "I don't think we can just say that the Hubble constant is 73, Friedman stated. "We don't yet, I think, have the evidence to unambiguously conclude that there's a tension. I just don't see it." Ries, reviewing Friedman's results, was not persuaded. He pointed out concerns about the small supernova sample used in one step of Friedman's analysis, arguing that this could bias the results. "The new measurements are lovely, and in fact are in excellent agreement with the same measurements obtained several years ago by our group, so the distance measurements seem under control," he said, while expressing concern about the sample selection issue. Nobel laureate Saul Perlmutter of UC Berkeley, who reviewed Friedman's preprint, framed the situation with elegant precision. "We may have a Hubble tension just within the star-based measurements. That's the tension that we really have to be trying to figure out, more than trying to invent new cosmological models." This is where the situation stands as of mid-2026. The Hubble tension has not been resolved. Webb has not killed it, and it has not confirmed it beyond all doubt. What Webb has done is sharpen the measurements, reduce some sources of systematic error, and in doing so, made it clearer that the remaining discrepancy is not simply a matter of bad data. Something is genuinely misunderstood, either in the distance measurements themselves or in the cosmological model. The most unsettling possibility, the one that would truly break new ground in fundamental physics, is that the model is incomplete. That there is an additional ingredient in the early universe, perhaps a form of dark energy that existed only in the first few 100,000 years of cosmic history and then dissipated, that affected the acoustic oscillations in the CMB in ways that changed the inferred value of h-Nero. This hypothetical ingredient is called early dark energy, and while it has been proposed and studied seriously, no definitive evidence for it has yet been found. The Hubble tension remains one of the most important open problems in physics and cosmology, and Webb's contribution to it has been to make it more precisely defined and harder to explain away, rather than solving it. There is a third area of discovery by James Webb that deserves deep attention, and while it is in some ways more nuanced than the galaxy formation and Hubble tension problems, it connects the telescope's work to the most profound question human beings have ever asked. Are we alone? Webb was designed to study exoplanet atmospheres, the thin envelopes of gas surrounding planets in other star systems, with unprecedented sensitivity, using a technique called transmission spectroscopy. When a planet passes in front of its star from our vantage point, a tiny fraction of the starlight passes through the planet's atmosphere. Different molecules in that atmosphere absorb specific wavelengths of light, leaving characteristic dips in the spectrum of starlight that reaches our telescopes. By analysing these dips, scientists can determine the chemical composition of a planet's atmosphere, what gases are present, in what proportions, and at what temperatures. The most anticipated targets for Webb's atmospheric studies were the planets of the TRAPPIST-1 system, a remarkable collection of 7 rocky, roughly Earth-sized planets orbiting a small, cool red dwarf star approximately 40 light-years from Earth. 3 of these planets, TRAPPIST-1, F and G, orbit within the habitable zone of their star, the region where liquid water could potentially exist on a planet's surface. The TRAPPIST-1 system had been the subject of intense scientific interest since its discovery in 2017, and Webb was seen as the instrument that could finally determine whether any of these planets had atmospheres, and, if so, whether those atmospheres showed any chemical signatures that might be associated with biological processes. The results from TRAPPIST-1 have been sobering, informative, and appropriately complex. Webb's observations of TRAPPIST-1b, the innermost planet, closest to the star and thus most exposed to stellar radiation, showed no evidence of a substantial carbon dioxide atmosphere. By detecting the thermal emission from the planet, scientists found that TRAPPIST-1b was hotter than it would be if it had a significant atmosphere to redistribute heat around the planet. The conclusion was that TRAPPIST-1b is most likely a bare rock, stripped of any thick atmosphere by the intense radiation from its host star. TRAPPIST-1c, the second planet, also failed to show evidence of a thick CO2-dominated atmosphere similar to Venus's. These results were published in Nature in 2023 and represented the first definitive atmospheric characterization of a TRAPPIST-1 planet. They were not the triumphant announcement of a potentially habitable world that many had hoped for, but they were scientifically rich in their own right. They told scientists something real about the fate of rocky planets orbiting red dwarf stars, which are by far the most common type of star in the galaxy. More recent Webb observations have continued to explore the TRAPPIST-1 system. TRAPPIST-1d has shown evidence suggesting only a thin atmosphere, if any. The more distant, potentially habitable planets, E, F and G, remain under study, with results expected in the coming years. The overall picture emerging from TRAPPIST-1 is one of caution about the habitability of planets orbiting red dwarfs. Red dwarf stars are active, producing intense ultraviolet and X-ray radiation during their early lives, and the inner planets of TRAPPIST-1 may simply have been stripped bare by this stellar activity over the billions of years of the system's history. This does not rule out the possibility that the outer planets retain atmospheres, but it makes the habitability question more complex and more difficult to answer than the initial excitement surrounding the TRAPPIST-1 system might have suggested. Meanwhile, in September 2023, Webb generated headlines around the world with observations of a completely different exoplanet, K2-18b, a world approximately 120 light-years from Earth, orbiting in the habitable zone of its host red dwarf star. K2-18b is not a rocky planet like Earth. It is a sub-Neptune, a planet significantly larger than Earth but smaller than Neptune, with a mass roughly 8 times Earth's. A 2023 study of K2-18b detected methane and carbon dioxide in its atmosphere, along with a potential detection of dimethyl sulfide, or DMs. On Earth, dimethyl sulfide is produced almost exclusively by living organisms, specifically by marine phytoplankton and other microbes. Its detection in a planetary atmosphere would in principle be a potential biosignature, a chemical indicator that life might be present. The team reporting this result, led by Niku Madhusudan of the University of Cambridge, suggested that K2-18b might be a Hycean world, a planet with a hydrogen-dominated atmosphere overlying a deep liquid water ocean, and that the potential DMs detection was intriguing in this context. The scientific community's response was measured and appropriately cautious. The DMs detection was described as tentative, a statistical hint rather than a firm detection, with multiple alternative explanations possible. Subsequent follow-up work has scrutinized the claim from multiple angles. A 2025 paper in Nature noted that the evidence for biological activity outside the solar system remains the strongest yet obtained, but simultaneously urged significant caution, acknowledging that non-biological chemistry could potentially produce DMs in a hydrogen-rich atmosphere under the right conditions. The uncertainty is genuine and reflects the appropriate scientific standard: extraordinary claims require extraordinary evidence. What the K2-18b observations demonstrate is not that alien life has been found, but that Webb has the sensitivity to detect potential biosignature molecules in exoplanet atmospheres at distances of 120 light-years, a capability that did not exist before Webb, and that opens a door to a kind of search that was previously purely theoretical. Over the next decade, as Webb accumulates more observations of more exoplanet atmospheres, the statistical framework for evaluating these potential detections will become much clearer. Webb's very first exoplanet atmospheric observation, conducted as part of its early release science program, targeted WASP-39b, a hot gas giant, much larger and hotter than Jupiter, orbiting extremely close to its host star roughly 700 light-years from Earth. WASP-39b is not a potentially habitable world, but it was chosen as a demonstration target because its large size and high temperature make its atmospheric features easy to detect. The results were extraordinary in their completeness. Webb detected carbon dioxide, carbon monoxide, water vapor, methane, sulfur dioxide, and sodium in WASP-39b's atmosphere, creating the most detailed and complete chemical portrait of an alien world's atmosphere in the history of astronomy. The sulfur dioxide detection was particularly significant because it represents the first time a molecule in an exoplanet atmosphere had been detected that is thought to be produced by photochemical reactions driven by the star's ultraviolet light, a direct indication that chemists could now study the complex dynamic chemistry driven by starlight in alien atmospheres. While WASP-39b is not a place where life could exist, the WASP-39b observations demonstrated that Webb was functioning beyond its design specifications, and that its atmospheric chemistry capabilities were everything its designers had hoped for and more. Let us step back now from the individual discoveries and look at the larger pattern they form, because there is a pattern here that scientists have noticed and that has become one of the central unsolved puzzles in observational cosmology. Across multiple independent lines of evidence, James Webb is consistently finding that the early universe was more organized, more structured, more evolved, more massive, and more chemically complex than our standard model predicted. The two massive galaxies, the overmassive black holes, the well-developed galactic structures at very early times, the Hubble tension, which points to a discrepancy in the expansion rate that may indicate missing physics in our cosmological model. Each of these individually might be explainable within existing frameworks through refinements and adjustments, but the fact that they all seem to point in the same direction, toward an early universe that was more highly organized than expected, is something that the scientific community is taking very seriously. In the summer of 2024, a review article that surveyed the accumulated anomalies found by Webb in its first 2 years of science operations used the phrase cosmic inconsistencies to describe the overall picture. This phrase captures the situation precisely, not a single catastrophic failure of the standard model, but an accumulation of inconsistencies, each one individually uncertain, but collectively forming a pattern that demands explanation. It is rather like going on a long hike through what should be familiar forest and finding, every few miles, a tree that doesn't belong there, a species that doesn't grow in this climate, or a tree that is far too old for a forest that is supposed to have regrown from a clear-cut 50 years ago. One such tree might be dismissed as an anomaly. 5 such trees in different locations starts to suggest that maybe the history of this forest is not what you thought it was. The honest and important answer to the question, is the Big Bang theory wrong? Is no, not in the way that phrase is usually intended. The Big Bang theory, the idea that the universe began in an extraordinarily hot, dense state approximately 13.8 billion years ago and has been expanding and cooling ever since, is supported by multiple independent lines of evidence that Webb has not in any way undermined. The cosmic microwave background radiation still exists exactly as the Big Bang predicts. The abundance of light elements, hydrogen, helium, and trace amounts of lithium in the universe is still consistent with the nucleosynthesis that occurred in the first few minutes after the Big Bang. The redshifting of distant galaxies still confirms that the universe is expanding. The large-scale structure of the universe, the cosmic web of galaxy clusters, filaments, and voids, is still broadly consistent with the hierarchical structure formation driven by dark matter that Lambda CDM describes. None of this is under serious challenge from Webb's observations. What is under challenge, or at least under renewed scrutiny, is not the Big Bang itself, but the specific parameterization of our cosmological model. The particular values we assign to the densities of dark matter and dark energy, the particular assumptions we make about the initial spectrum of density fluctuations after the Big Bang, the particular models we use to describe how galaxies form and evolve within dark matter halos. These are not the foundational pillars of Big Bang cosmology. They are refinements, additions, and elaborations built on top of those pillars, and it is those refinements and elaborations that Webb's observations are, in some cases, straining against. scientists are now seriously exploring several categories of extensions or modifications to the standard model that might help explain the anomalies. One possibility is that dark matter is not precisely cold in the way lambda CDM assumes, that the actual particles constituting dark matter might have properties slightly different from the cold, collisionless, pressureless dark matter assumed in the standard model, and that these different properties might affect how quickly dark matter halos form and how efficiently they accumulate baryonic matter to form galaxies. Warm dark matter, which has slightly more velocity and therefore slightly more ability to stream out of small gravitational wells, would suppress the formation of small structures while still allowing large ones to form, potentially relevant to the galaxy formation anomalies, though current constraints make this explanation difficult to reconcile with all the data simultaneously. Another possibility being explored is that the process of star formation in the very early universe was significantly more efficient than in later epochs, that in the dense, metal-poor, turbulent environments of early universe clouds of primordial gas, stars formed at rates much higher than any later epoch, consuming gas rapidly and building up stellar mass quickly. Some researchers have proposed that the initial mass function of stars, the distribution of stellar masses produced in any given burst of star formation, may have been skewed in the early universe toward more massive stars, which burn brighter but faster. A galaxy full of extremely massive, extremely luminous stars would appear far more massive than it actually is in terms of total stellar count, potentially explaining some of the apparent excess of massive galaxies without requiring a fundamental change to the cosmological model. This top-heavy initial mass function hypothesis is actively being investigated, and Webb's observations of individual stellar populations in the most distant galaxies may eventually be able to test it directly. The early dark energy hypothesis, previously mentioned in the context of the Hubble tension, represents a more radical modification of the standard model. It proposes that a brief period of enhanced dark energy existed in the early universe, before the universe was about 100,000 years old, that temporarily sped up the expansion rate during the epoch when the acoustic oscillations that show up in the CMB were being set up. This extra energy would have modified the acoustic scale slightly, causing the CMB-based inference of h-Nero to be artificially low compared to the true expansion rate. Early dark energy models have been scrutinized extensively and remain controversial, with some observational tests supporting them and others constraining them. Webb observations have not definitively confirmed or ruled them out. What makes all of this particularly exciting from a scientific perspective, and what often gets lost in media coverage that gravitates toward either extreme of Big Bang proven wrong or nothing to see here, move along, is that this is science working exactly as it should. A new, more powerful instrument reveals phenomena that the existing best theories struggle to account for. Scientists respond by checking and rechecking the observations, by developing new theoretical frameworks, by testing those frameworks against additional data, by following the evidence wherever it leads. The history of physics is full of moments like this, moments when observations pushed past the boundaries of the existing framework and required genuinely new thinking. The discovery that the orbit of Mercury did not quite match Newtonian predictions led eventually to general relativity. The discovery that atomic spectra had a precise, discrete structure led eventually to quantum mechanics. The discovery in 1998 that the expansion of the universe was accelerating rather than decelerating led to the concept of dark energy and the modern lambda CDM model. Each of these moments of apparent breakdown turned out not to be the destruction of science, but its expansion, science stretching to accommodate reality rather than insisting that reality fit neatly into previously established boxes. The human beings driving these investigations deserve recognition, because science is ultimately a human enterprise conducted by people who have dedicated their careers and their intellectual passions to questions that will not be fully answered in their lifetimes. Ivo Labi, whose team first reported the universe breaking galaxies, has spent years carefully following up those initial observations with more precise spectroscopic measurements, refining and correcting earlier estimates, making the science better through the patient work of verification. Joel Lehr, whose informal coining of the term universe breakers captured global attention, continues working to understand what these extraordinary early galaxies are actually telling us about the physics of the early universe. Wendy Friedman, who has spent more than 2 decades pursuing the most precise measurement of the Hubble constant ever made, used Webb's capabilities to mount a sophisticated multi-method analysis that has added enormously to our understanding of the problem, even while failing to definitively solve it. Adam Riess, whose Nobel Prize-winning work on dark energy already represents one of the greatest cosmological discoveries of the 21st century, continues to push the precision of his H-Nero measurements, confident that the tension is real and pointing to genuinely new physics. Ekos Bogdan, who led the team that identified UHC1, has helped establish the empirical foundation for the direct collapse model of black hole formation that may resolve one of the deepest mysteries in galaxy evolution. Jane Rigby, Webb's operations project scientist at NASA's Goddard Space Flight Center, has been the public face of the telescope's science operations since its launch. An openly gay scientist who has spoken about the intersection of identity and scientific vocation, Rigby has communicated Webb's results to the public with a combination of deep expertise and genuine enthusiasm. Her work coordinating the complex logistics of a multi-institution, multi-country scientific program, while ensuring that the telescope's time is allocated fairly and its observations are executed efficiently, represents a different kind of scientific achievement, the organizational and institutional infrastructure that makes individual scientific breakthroughs possible. Without people like Rigby managing the operational complexity of an instrument like Webb, the discoveries we have been discussing would remain theoretical possibilities rather than empirical realities. The telescope itself, meanwhile, continues to exceed expectations. Its fuel reserves, spared by the precision of the Ariane 5 launch in December 2021, mean that Webb is now expected to remain operational for at least 20 years and possibly longer. The original 10-year design lifetime was already going to be extraordinary. 2 decades could be transformative. In the time remaining to it, Webb is expected to complete a systematic survey of exoplanet atmospheres in the TRAPPIST-1 system, reaching the potentially habitable outer planets, whose atmospheres have not yet been fully characterized. It is expected to observe increasingly distant and early galaxies, pushing back the redshift frontier toward the first few 100 million years after the Big Bang. It is expected to contribute further measurements relevant to the Hubble tension, with Friedman and Rees both promising improved precision in the coming years as their respective analyses incorporate more and better data. It is expected to study the formation of planets in our own galaxy in ways that were previously impossible by imaging planetary nurseries. Disks of gas and dust around young stars, with a resolution and sensitivity that makes the individual chemical components of those disks legible for the first time. Alongside Webb, the next generation of ground-based telescopes is coming online. The Extremely Large Telescope, being constructed by the European Southern Observatory on Cerro Armazones in Chile's Atacama Desert, will have a primary mirror 39 meters in diameter, larger than any existing telescope by a substantial margin, and will be capable of following up Webb's discoveries with complementary spectroscopic observations that can further characterize the objects Webb has found. The Giant Magellan Telescope and the 30-meter telescope are also in development, and together with Webb, they will form an observatory ecosystem of unprecedented power for studying the universe across all cosmic epochs. NASA's Nancy Grace Roman Space Telescope, which will be a wide-field infrared survey instrument, is planned for launch in the late 2020s and will complement Webb's deep-field observations by surveying much wider areas of sky, enabling statistical studies of galaxy populations across cosmic time that will be essential for testing the cosmological models that Webb's deep observations are challenging. And that is perhaps the most important thing to understand about where we stand today in the wake of Webb's first 3 years of science. We are not at the end of the story. We are deep in the middle of it. We are at one of those rare, precious, historically significant moments when the boundary of human knowledge has been pushed into genuinely new territory, when the instruments we have built have outpaced the theories we have developed, when the universe is showing us things that our best models did not predict and that our best minds are still working to understand. The fear that James Webb has created in the scientific community is not the fear of failure or the fear of being wrong. It is the fear that comes with wonder, the vertiginous feeling of standing at the edge of the known and looking into the unknown, of realizing that the universe is larger and stranger and more complex than you had imagined, and that the models you built with such care and precision, while correct in so much, are not yet complete. Consider what these discoveries mean for the deepest questions about reality. If the first massive galaxies in the universe assembled far more quickly than our models predict, it means that the processes governing how matter organizes itself in the aftermath of the Big Bang are not yet fully understood. If the Hubble tension is real and represents not a measurement error, but a genuine discrepancy between the early and late universe expansion rates, it means that the inventory of the universe, the precise accounting of dark energy, dark matter, and ordinary matter that governs cosmic evolution, may be missing an ingredient that existed early in cosmic history and has since disappeared or changed. If the first supermassive black holes formed through direct collapse of primordial gas clouds rather than through the slow accretion of stellar mass seeds, it means that the universe in its youth had pathways for creating extreme concentrations of mass that no longer operate in the cosmos we inhabit today. Each of these implications points in the same direction. The universe has a more complex, more varied, more interesting early history than we previously knew. There is something genuinely moving about the fact that human beings, on this small rocky planet, orbiting an ordinary star in the outer spiral arm of a completely unremarkable galaxy, have built a machine that can capture photons of light that left the universe when it was only 3% of its current age. And from those photons read the history of how the first stars and galaxies came to exist. The golden mirror of James Webb, floating serenely at the second Lagrange point 1.5 million kilometers from Earth, surrounded by the eternal cold of interplanetary space, does something that no other object in human history has done. It sees the universe as it was before Earth existed, before the Sun was born, before the Milky Way had taken its current form, before any of the carbon or oxygen or iron in your body had been forged in the hearts of long-dead stars and scattered by their explosive deaths. It sees the raw material of everything you are and everything you see, in the process of assembling itself for the first time. That the universe revealed through that golden eye does not quite match the expectations of our best theoretical models is not a failure of science. It is the most exciting possible outcome of scientific inquiry. It means that there is still discovery to be made, still mystery to be illuminated, still genuine surprise waiting in the data. It means that the universe is more than we imagined, more than we modeled, more than we predicted, and that the process of understanding it, the long, patient, rigorous, self-correcting process of science, still has a great deal of work to do. The fear that James Webb has created in the hearts of cosmologists is not the fear of a nightmare. It is the fear you feel standing at the rim of the Grand Canyon for the first time, or at the edge of an ocean whose opposite shore you cannot see. A fear that is indistinguishable from awe. A fear that comes not from danger, but from scale. From the overwhelming realization that the thing before you is larger and deeper and more magnificent than you had prepared yourself to encounter. The 6 candidate massive galaxies that Joel Layer called universe breakers are still being studied. Some of their initial mass estimates have been revised downward. Some have been confirmed as real massive structures at extreme distances. The debate continues, carefully, methodically, through the proper channels of peer review and replication. The Hubble tension remains unresolved, with 2 world-class teams of scientists and their respective sophisticated methodologies pointing at modestly different values of the same fundamental constant, and neither able yet to definitively demonstrate that the other is wrong. The little red dots remain mysterious, potentially compact galaxies, potentially overmassive active galactic nuclei, potentially a new class of object that has never been observed before, and that will require both new observations and new theoretical frameworks to understand. UHZ-1 sits 13.2 billion light-years away, its black hole blazing with X-ray radiation in data captured by Chandra, its host galaxy identified in Webb's infrared images, representing the earliest and most direct evidence yet obtained for the direct collapse pathway of black hole formation. Each of these stories is still unfinished. Each will continue to evolve as more observations are collected, as more precise measurements are made, as more sophisticated analyses are applied. The answers, when they come, will be more nuanced than the dramatic headlines might suggest. They may not require abandoning lambda CDM entirely. They may require modifying it, extending it, adding new physics at the boundaries where it currently struggles. Or they may ultimately require something more radical, a genuinely new theoretical framework that encompasses lambda CDM as a limiting case the way general relativity encompasses Newtonian mechanics, valid within a certain regime but incomplete at the boundaries. We do not yet know which of these outcomes awaits us. We are in the middle of the scientific process, not at its end. What we do know, with certainty, is that James Webb has already done what it was built to do. It was built to push the limits of human knowledge about the origin and evolution of the universe, and it has done so in its very first years of operation in ways that no one fully anticipated. It was built to see the first light of the universe, and it has seen structures in that first light that challenge and enrich and complicate our understanding of how the universe grew from the simplest of beginnings into the extraordinary complexity of the cosmos we inhabit today. It was built to study the atmospheres of worlds that might potentially harbour life, and it has detected chemical signatures in those atmospheres that, while not yet confirmed as signs of life, represent the first real steps toward an answer to the oldest question of all. And it was built to last, built with enough fuel reserves to operate for 2 decades, built with enough scientific ambition to generate discoveries for a generation of astronomers, and in all of this it has already exceeded the hopes of the scientists and engineers who spent 25 years of their professional lives bringing it into existence. The universe, it turns out, is under no obligation to conform to our expectations. It does not care about our models or our timelines or our theoretical predictions. It simply exists, in all its staggering, lawful, mysterious complexity, waiting for us to build good enough instruments to read its history correctly. James Webb is the best instrument humanity has ever built for that purpose, and what it is telling us, across every line of evidence, across every redshift range, across every type of object and every category of observation, is that the universe's history is richer, more complex, and in some ways more surprising than we knew. That is not something to fear in the sense of being frightened. It is something to embrace, with curiosity, with rigour, with humility, and with the profound gratitude of creatures lucky enough to live in an age when the tools to ask these questions and to begin hearing their answers actually exist. If you have followed this story to its end, through the golden mirror of Webb and the Christmas launch and the 29 days of terror, through the universe-breaking galaxies and the Hubble tension and the little red dots and the 2 early black holes and the alien atmospheres, then you have done something remarkable. You have sat with one of the most complex and honestly uncertain scientific narratives of our time, and you have let it be what it is, unfinished, complicated, and full of genuine mystery. You did not need easy answers or false certainty. You were willing to sit with the questions themselves, and that is exactly what science asks of all of us, not the false comfort of premature conclusions, but the more demanding and more rewarding practice of honest inquiry sustained across time. The universe is 13.8 billion years old. James Webb has been operating for 3 years. The conversation between this telescope and the cosmos is only just beginning. What it will say next, no one knows. But the scientists watching the data streams from that golden mirror, floating silent and cold and infinitely attentive at the gravitational equilibrium point between Earth and Sun, are listening with everything they have. And so, now, in some small way, are you. If this journey through the cosmos moved something in you, If some part of this story made you look up at the night sky with different eyes, then share it, because these questions belong to everyone. Leave your thoughts in the comments. Which of these discoveries unsettled you most? Was it the galaxies that appeared too soon? The expanding universe that can't agree with itself about how fast it's moving? Or those mysterious little red dots, those strange compact objects blazing in the early universe, waiting to be understood? Whatever your answer, the conversation continues, and the universe, patient and vast and full of secrets it has not yet finished revealing, will be waiting. End.